Welcome to The Edge of Knowledge with Lawrence Krauss. We are very excited to have him here in Orange County, and we hope you enjoy his lecture. There will be an intermission after he finishes the first part, and you'll be encouraged to write down questions that you'd like him to address in the second part of our program. So I hope you enjoy it and have a good time.
Thanks, Sandy. Thank you, Andy. I think this one works, and this works too. Good. Thank you. I've met many of you out there, and it's nice to see you here. It's a lovely venue, and so it's really nice to have a kind of intimate conversation. And as I told some of you, and this is the first lecture I've really given on the new book, the first full-on lecture, so you're guinea pigs. But I find it's particularly appropriate to talk about this book for this group and for the Origins Project Foundation, because we're kindred spirits. The book is about mysteries, and this is one of my favorite quotes from Richard Feynman, which is at the beginning of the new book. And I don't feel frightened not knowing things, by being lost in a mysterious universe without any purpose, which is the way it really is as far as I can tell. And our Origins family is all about that. It's people who are not afraid of not knowing things, because that's an invitation to discover. And we try and do that with our events like this and the podcast, where we try and bring together the most exciting people from today, talking about issues that are incredibly important for the 21st century and beyond. And it's really the origins of the future in that sense. And with our trips, a number of the people here have been on our Origins trips, and the board members may have talked to you about it, that our next trip is in the Galapagos. And I think the trip after that will be in Bhutan. So go to the Origins website and come join us. And in any case, so I think this lovely mixing of mystery and excitement is particularly appropriate to introduce here in this place. So I want to talk about that. I often show these two pictures because I think it puts in perspective of how much things have changed. When I started to write the book, my British publisher reminded me of a book by Sir James Jeans in 1930, which was called The Mysterious Universe. And almost everything in that book is now out of date. And this was the universe, not as well observed as it is here, because this is a beautiful telescope picture of the Andromeda galaxy, the nearest large galaxy to our own, about 2 million light years away. But it looks like our own galaxy would look like this if we were out at Andromeda. But the important thing is, in 1923, that was it. People didn't know of they didn't even know of the Andromeda galaxy. They only knew of our galaxy. The Milky Way was the universe. And 80 years later, 100 years ago, but 80 years later, this is a picture from the Hubble Space Telescope, and I was going to show a James Webb picture, but it doesn't look that different. It's a little more resolved, but we know, except for that, in this particular image, except for that's a star. Every dot, every point of light in that image is a galaxy. There are more than 100 billion galaxies in the observable universe, and in an 80-year period, it changed from 1 to 100 billion. The mysteries of the universe are profound and evolving, and I certainly hope that 80 years from now, after the publication of my book, that the mysteries will have dramatically changed. And it'll change because people are interested in keeping asking questions. Scientists and the public who want to support science and who want to support progress by being willing to ask any question, regardless of how uncomfortable it might be to ask that question, and is not afraid to search for the answers. In any case, I think the book divides into 5 pieces, and I want to pick an example from each piece. And I think the first one is probably the area that it touches us most, time. It's the most personal of all the things. Time is an essential part of our lives. Lost time we wish we'd regain, I think for the beginning of each chapter, I have a quote, and this one, Kurt Vonnegut always puts things very well. He said, "Here we are, Mr. Pilgrim," except I spelled it wrong, "trapped in the amber of this moment. There is no why." We all are trapped in the moment of time, and the big question is that an illusion or not? Some philosophers, some physicists think time may be an illusion. I always think that's kind of a useless thing to say, because it doesn't really matter if it's an illusion. If you miss the 5:10 train to work and you lose your job, it's not an illusion. And the question is, if it is an illusion, the really interesting thing is, how did it come about? And time is still, among all of the fundamental quantities in the universe, probably the most mysterious quantity, because it begs so many questions. But our picture of time itself, of course, has changed a lot in the last century. And we'll see if I have to stand closer to get it to go. There we go. Before I had my iWatch, I wrote one of my books when I used to visit Zurich in Switzerland, and I always was desperately worried that my watch was wrong, because I would take the train in, and the Swiss trains are exactly on time. And so I knew what time it was by getting to the train station and seeing if I'd missed my train. And now we all have atomic clocks on our hands, so it doesn't really matter. But Switzerland is obsessed with time in that sense, because the trains go everywhere. From any spot in Switzerland, there's a train leaving every 2 minutes or so. And that's not inappropriate when talking about time, because the nature of time was changed by trains. It used to be in Switzerland and throughout Europe that each canton, each city had its own time zone. And that was okay when you were traveling by horse. But once trains were created and you could go from city to city quickly, it became very inconvenient to have many time zones, and regularizing time became essential. And of course, that's what slowly happened. Now, that regularization of time was important in the sense of trains, and it was also important for someone who worked right opposite this big clock. This is in Bern, Switzerland. And Albert Einstein worked in a patent office, and every day he could not only see the clock, but the train station. And he changed our picture of time and space forever. And it's not surprising that when he began to think about how to describe the new sense of time, he used trains to do it. And what he realized is that, well, time may be an illusion, but we know the time that happens to us is quite personal. And the time that happens to you is quite personal. But I make the assumption every day that your time is my time. That when I'm reading the clock at 7 o'clock, that you're reading the clock at 7 o'clock. But it's an assumption, because I can never be in two places at once. And Einstein spearheaded the notion of thinking operationally. What can you actually measure? And realized that, in fact, this assumption that my time and your time are always the same is wrong. And he showed it was particularly wrong when things speed up. And the example he gave was what involved a train. And I'm not going to go into the details of relativity, except to point out one of the consequences of relativity, or actually two, as you'll see in a moment, one from special relativity. So let's say we have a train, and the conductor has gone through the train and synchronized all the clocks. So they're all ticking at the same rate. On the train, it's 12 o'clock noon on one end of the train, and it's 12 o'clock noon on the other end of the train at the same time. What Einstein's theory of relativity showed, and it's true, in spite of the fact that it may seem crazy, is if that train is moving very fast relative to us and we're watching it, two things happen. You notice the train is squished up. It's actually smaller than it looks like when it's standing still. You might say that's just perception, but it's not perception. It is smaller for you. It's not smaller for the people on the train. Both sets of people are right. But the other thing that's particularly weird is that you can look at those clocks that were synchronized, and you find that they're not synchronized anymore. That if it's that the clocks on the front of the train are actually ahead of or the back of the train are actually ahead of the clocks on the front of the train. So if it's 12 o'clock on the front of the train, it could be 12:01 on the back of the train. This, of course, begs all sorts of questions about causality, because if two things are simultaneous for me, but they're not simultaneous for you, if one event happens after another event for me, and for you, one event happens before the other event, then all sorts of notions about causality seems to go out the window. It turns out they don't. There's a kind of cosmic catch-22 that I won't go into. But what it became clear was that time was relative, as is space, and it depended on your state of motion, and what you presume other people are measuring in terms of time can be wrong. Now, this was all hypothetical when Einstein developed relativity, because he couldn't measure these factors. We can now measure these effects every day in undergraduate physics laboratories. But there's another effect of time that didn't come from his special theory of relativity, but his general theory of relativity. And it was actually demonstrated. I used to work, and this was at Harvard. This was my office in Harvard, Jefferson Labs. And in the 1960s, physicist Robert Pound and his colleague did an experiment to demonstrate an effect that Einstein's general theory of relativity had predicted. Special relativity tells us that clocks tick at different rates depending upon your state of motion. General relativity says that gravity changes time. And my clock now is ticking at a different rate than your clocks, because you're closer to the center of the earth than I am right now. The effect is so minuscule that you could never figure you could measure it, but Pound and his colleague did that by using in the old days, they had a radioactive source in the basement of Jefferson Lab, and then they used telephones to talk from the basement to the roof, and iron, when it's radioactive, emits a very specific frequency of gamma rays. And what is still amazing to me is that the predicted difference between the rate of clocks from the bottom of the Harvard Jefferson Labs to the top was 1 part in 10 to the 15th. 1 part in a million billion. That's the difference. But they actually were able to measure it and confirm Einstein's theory. Now, I mention this, and it's particularly appropriate to do it in Los Angeles, because this all sounds neat and esoteric, but completely divorced from your own experience. But it turns out it's not. About 15 years ago, I was stuck in traffic in Los Angeles, which happens, as you all know, and I wrote an article about being stuck in traffic in Los Angeles. I don't think I actually wrote it while I was stuck in traffic, but it's quite possible I may have. And you use this fact, this obscure fact, every day. Many of you used it to get here. Okay? Because global positioning satellites, which are all our phones, our smartphones use to get us places, work by using time. You have a number of satellites, and the satellites send signals back and forth to your phone, or another way of putting it is your phone detects signals from the satellite and sends a signal back. And there are many satellites. They're located up, they're moving about 8,000 or so miles per hour. Some of them are 20,000 miles above the Earth's surface. And you find out where you are by triangulation. You have to see more than one satellite. But if you know where the satellite is, and you know the length of time it takes for the signal to bounce between the satellite and you can figure where you are on this line. Similarly, if you could do the same thing with here, you can figure out where you are on that line, and seeing where they intersect tells you where you are. That's how global positioning satellites work. They only work because they have atomic clocks. Because light travels so fast that even up at 20,000 miles, it takes a fraction of a second for light, which travels at 186,000 miles per second in an obscure set of units that only the United States and England use. But in any case, so it takes a fraction of a second to do that, and they have to have atomic clocks so that the time is accurate. But those clocks are moving fast, 8,000 miles per hour or so, which tells us that special relativity tells us that those clocks are ticking at a different rate than here. But it turns out that effect is minuscule compared to the other effect that these clocks are high above the Earth. And it turns out when you work out these two effects, these clocks here at different places would be ticking about 38 microseconds per day faster than the clocks on Earth. Now, light travels at a meter in a billionth of a second, 1/1000th of a microsecond. Okay, so if we did not take into account general relativity and adjust for the fact that these clocks are running at a different time because they're high up, within a minute, your GPS would be out by a kilometer. So it's not esoteric at all. It governs your lives to the extent that you use GPS. In LA, I imagine most people govern their lives using GPS, trying to figure out how to go off the freeway and find to where they're going. Okay? So this obscure aspect of time is really part of the central part of our existence, something I'll come back to later. Technology changes not just the way we think about the world, but the way we act. And this fact that time changes due to gravity, as does space, is part of the central feature of general relativity, which is that time and space are really different aspects of the same thing. We live in something called space-time. But if time and space are really different aspects of the same thing, that begs an important question, which a lot of people are interested in, maybe more than GPS, which is, can you build a time machine? This is one of the known unknowns, one of the edge of knowledge questions, because the answer to this question is we don't know. That's what makes it so neat. We don't know. We do know, look, it seems in general relativity like it should be possible because I could take a trip to Los Angeles and back, go a round trip in space, and if space and time are really the same, why can't I do a round trip in time? General relativity says you can. You can do a round trip in time, in principle. But can we do that in practice? We don't know. It turns out I can even draw a time machine. This is one kind of time machine. It's called a wormhole. This is a two-dimensional representation of a curved three-dimensional universe. So all I can draw, and I didn't draw this in the first place, but it's all that we can draw. And as you know, if you saw the movie Contact, a wormhole is a shortcut through space. If space is curved, a wormhole could just be, take you in a mile, what might otherwise be thousands of light years away. Wonderful. But it turns out we can prove that a wormhole, if a stable wormhole can exist, then you can travel in time. Because it turns out if this end of the wormhole is moving through space fast, then a clock at this end of the wormhole is ticking at a much slower rate than a clock at this end of the wormhole. And it's moving in a big circle of 5 light years around. And you can find out that the clock here will be 5 years behind the clock there. And so all you have to do is go through the wormhole, you come out 5 years earlier. And let's say you have a really fast ship and you come back and you arrive at home a year before you left. All of that's possible in general relativity, in principle. The question is it possible in practice? And the answer is, what's the answer? I don't know. Perfect. You got the right idea. Because we can prove that you can't make wormholes out of normal matter. Kip Thorne actually was the one with his colleagues that proved that if you have normal matter and energy, then the mouth of a wormhole at either end will collapse to form a black hole in a time shorter than it takes to go through the wormhole. But maybe there are kinds of matter and energy that are different than the kind of matter and energy that we know of. Can you create those in the laboratory? And the answer is, we don't know. That's the open question. It depends on quantum mechanics, which I'll talk about, and general relativity, and we don't know if time travel is possible. General relativity allows it in principle. Most of us think it's probably impossible because of all the paradoxes that would result if you had time machines, like going back in time and killing your grandmother before you were born, and your mother, who would want to kill their grandmother? I know no one would want to. But and then your mother wouldn't be born, but then if she wasn't born, you wouldn't be born, and then how did you go back in time and kill your grandmother in the first place? The kind of thing gives people headaches. Stephen Hawking, my late friend Stephen Hawking, wrote the foreword for my book, The Physics of Star Trek. and he had said time travel was impossible. He actually tried to demonstrate it. He actually had a party in his house once. He invited time travelers from the future. No one showed up. He said that was proof. But I countered to him saying they all went back to the 1960s and no one noticed. But it's really an open question. And if time, the neat thing about this, of course, is that a universe with time travel seems ridiculous, seems impossible. But that doesn't matter. The universe doesn't care what seems impossible to us, what we find palatable or likable. The universe is the way it is. That's the great thing about science. Whether you like it or not, the universe is the way it is. And so this open question remains an open question. And maybe 100 years from now, there'll be a book that will be able to talk about another open question and say, well, we now know about time machines. But time, it amazes me that this fundamental, really nothing more central to our existence than time, key facets of it still remain open questions. And I love that. And anyway, so that's time. Space, not really the final frontier. But I think my quote is from another one of my favorite authors. There we go. You know this quote from Douglas Adams, maybe. Space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemist, but that's just peanuts to space. And he did, when he wrote Hitchhiker's Guide to the Galaxy, he had no idea, because space is much bigger than even he thought it was. To describe that, I have to spend a minute or two, a brief history of time and space. This is a history of the universe on a slide. And there's a lot there, but we won't go through it. But this is today, and this is going back in time. This is today when the universe is 13.8 billion years old. This is the Big Bang. The Big Bang, we really don't know what happened because the laws of physics break down there. But we can start talking about what happened shortly thereafter, and we can talk about it with a straight face. And what we've discovered is, as far as we can tell, there's no way to understand the properties of the universe that we see today, why the universe looks the way it does, why it's so uniform, and yet why there are galaxies and when they formed the way they did, unless at a very early time after the Big Bang, the universe underwent an incredible expansion, something we call inflation. It expanded by an unbelievable amount, more than 30 orders of magnitude in size, in a time period of a millionth of a billionth of a billionth of a billionth of a billionth of a second. Unbelievable. But it turns out naturally possible, and in fact, it's hard to make it not happen, given the laws of fundamental physics we now know. And then after that, well, the expansion happened, and then inflation had to end, because if that expansion didn't end, wouldn't be here. That's an important point in a moment. And then we had the hot Big Bang. After inflation ended, the universe got hot. It was a hot soup of elementary particles, with the ones we know of, and maybe dark matter. And then around the time when the universe was about 1/10,000th of a second old, the particles we know of began to form. Quarks combined to make protons and neutrons. And at the time when the universe was about between 1 second and 100 seconds old, the elements began to form, the light elements, hydrogen, helium, lithium. Those are the only elements that formed in the Big Bang. All the rest of the elements were created later in the cores of stars. And but, and this is the really amazing thing, this is why we know the Big Bang really happened, one of the many reasons, is we can measure nuclear reaction rates in the laboratory, the same nuclear reactions that would have eventually formed hydrogen, helium, and lithium. And we can predict, if the early universe was hot, about 10 billion degrees when it was 1 second old or so, how much hydrogen, how much helium, how much lithium, and it turns out the amount we predict changes vary by over 10 orders of magnitude. 25% of the universe should be helium, and 1 part in 10 billion of the universe should be lithium. Guess what happens when we look out at the universe? 25% of the universe is helium, roughly 1 part in 10 billion of the universe is lithium. That's one kind of set of examples, and many sets of observations that tell us this isn't just some theoretical construct. We can test it. So we know we certainly can study the universe back to at least 1 second. It turns out with the Large Hadron Collider, we're going back to try and understand and see the physics of what the universe was like when it was 1/10 billionth of a second old. And as we do more experiments, we can probe earlier and earlier into the history of the universe. Okay. And then, then after, when it was about 300,000 years old, something called the cosmic microwave background formed, which we can see and tells us a lot about the universe. Then when the universe is about 1 billion years old or less, the James Webb Space Telescope is now saying less. And I'm happy to talk about that because I know you've been reading some articles that claim things that I'll be happy to talk about. That galaxies form maybe a few 100 million years after the Big Bang. And then we're here and I'm talking. So that's the history of the universe. But this early period determines everything. It's amazing and often unheralded that if this is really right, then quantum mechanics, which I'll talk about a little bit later, which seems so strange, shouldn't be as strange as it is, because it turns out if inflation happened, then scales that were once so very small that quantum mechanics was important get puffed up to large scales. And in fact, those quantum fluctuations in space and time and matter in the early times eventually we can predict what will happen, and they'll produce little teeny lumps in energy and density that will eventually collapse to form galaxies, and we can measure them as hot and cold spots in the microwave background. And inflation predicts that quantum mechanics gives exactly the kind of spectrum of fluctuations that we see in the microwave background, which eventually produced galaxies, planets, stars, planets, and you. So when you want to know about what quantum mechanics looks like, look around the room. All the lumps in the universe originated as little quantum mechanical fluctuations, and inflation. It's one thing. But the other thing that's relevant for our understanding of space is, I talked about inflation beginning, and then I talked about it ending, but we really don't know how to make it end everywhere. In general, inflation keeps happening. It never ended. It's still going on. But we're here. What inflation suggests is that the universe isn't a universe, it's really a multiverse. Namely, what happens is like raindrops condensing out in the sky. Inflation is happening, but locally in some place, due to some interesting physics, you leave inflation and produce a hot Big Bang. And then the space between outside of our universe is still expanding incredibly fast. And then maybe later on or earlier, at some other point, the same thing happens somewhere else, and the same thing may have happened somewhere else. But interestingly, as you leave inflation, it turns out the laws of physics in each universe can be different. In some universes, you'll have galaxies. A lot of them, a few of them. In some universes, you won't. And that idea of a multiverse changes everything. It could be that the reason I went into science was not a good reason. I went into science to learn why the universe had to be the way it is. Okay? But it may just be an accident. It could be that there are an infinite number of universes over an infinite amount of time, and every different kind of law of physics can happen in those different universes, and those fundamental quantities that we try to understand as physicists might just be an accident of our existence. And maybe we'll come back to the implications of that for life in a bit. But you see, poor Douglas Adams was just thinking of one universe as being darn big. And now, if we're right, there can be, as I say, over an infinite amount of time, if inflation continues infinitely long, an infinite number of universes that develop. And the point is, they're causally disconnected from us. Space is expanding faster than the speed of light between these distant objects, which is allowed. Space can do whatever the hell it wants in general relativity. And so we'll never be able to see them directly, but they may exist. Now, that sounds like metaphysics, and it is. But it turns out there may be ways we can indirectly prove that they exist. In fact, I've proposed in some papers with a friend of mine, Frank Wilczek, about how to measure things that would tell us, we won't be able to measure them directly, but if what we measure is there, it will tell us that they must exist. It's not too different than a little over 100 years ago in 1905, when Einstein wrote 4 papers, one of which, for his PhD thesis, proved that atoms existed. At the time, it's interesting to realize that in 1900, atoms were kind of mathematical creations and people used them, chemists used them, but there was still a huge debate about whether they were real. And Einstein showed by using something called Brownian motion, you could infer that atoms exist and even estimate their size, but no one ever thought you'd see an atom, ever. Now we can actually see them with our fancy kinds of electron microscopes and other kind of microscopes. So the situation is very similar. Everyone recognized by 1905 or 1908 that atoms existed, even though they knew they'd never see them. Maybe one day we'll be able to make measurements of gravitational waves, it turns out, new measurements of gravitational waves that will give us a direct indication that those other universes actually exist, even though we'll never be able to see them. Right now, we don't know. It's an open question, one we want to answer. Well, that's it for space. Now I want to talk about matter. And what quote do I have for this? Yeah, I like this. Dirt is not dirt, but only matter in the wrong place. Anyone who gardens knows that. And my friends in Phoenix know that a lot. There's a lot I could talk about matter. You might think I'm going to talk about some of thermophysics, but what I want to do is disabuse you of one of the many popular, I won't say fallacies, but popular misconceptions that are in the literature about quantum mechanics. People love to write about the weirdness of quantum mechanics because it is weird. I want to show you now that it's weirder than you can imagine, but the stuff you read about it all is misplaced. So I want to explain quantum mechanics. Well, I want to demonstrate quantum mechanics. I might not explain it. And I want to do it. A late colleague of mine at Harvard, Sidney Coleman, who was a remarkable physicist, an incredibly funny guy, and brilliant. Certainly the smartest guy at Harvard when I was there. And when I was there were 8 Nobel laureates, but he was smarter than any of them. He gave a lecture called Quantum Mechanics in Your Face, which changed my own picture of quantum mechanics. And I just want to show you, a lot of people think the quantum world is weird, but really that's just an accident because we really can't see the fundamental world. If it's just an illusion. If you could really probe the world on a basic level, it would be sensible. It wouldn't be quantum mechanical. And there are experiments you can do. In fact, the year before this, the Nobel Prize was given for people who demonstrated the certain fundamental characteristics of quantum mechanics, like entanglement and other things. And I want to show you one of the ways that you can prove that the universe isn't sensible. Okay? And it involves this experiment which he described here. So you take 3 different observers. They're located, San Diego, Los Angeles, and San Francisco, let's say. And you have a central laboratory, and it sends out something to those 3 observers. And there are 3 laboratories. And each of those laboratories has what Sidney called the little Acme Little Wonder dual cryptometer. Okay? And what that is it turns out, whatever this is, it will cause your detector, which can measure one of 2 things, A and B, and you don't know what those things are, A and B. You're given the black box. And you say, you choose whether you're going to weather A or B each time this experiment is done, and record your answer. It turns out A or B can be plus or minus 1. If you look on the right side of the detector, you'll measure A, the A property. If you look on the left side of the detector, you'll measure the B property. You choose. Each of the experimenters choose. They can't communicate with the other experimentalists because they're far away. So there's no interaction between the experimentalists. Okay? Good. Now, let's just say observer number 1 measures property A. Observer number 2 measures observer number 1 measures property B. Observer number 2 measures property A. Observer number 3 measures property B. So 2 observers measure B and 1 observer measures A. Well, there's obviously 3 different ways to do that. And I'll draw them here. You can just figure out either A is measured there, A is measured there, or A is measured there. Fine. Now, say you do those measurements and you find the following. It turns out, always, every time you do the experiment, if 2 people happen to measure B and 1 person happens to measure A, again, it's random, they're not communicating with one another, you multiply what they measure. Remember, each thing they're measuring can be plus or minus 1. You always get plus 1. Now, you have to prove this to yourself. It's a homework assignment. I'm not going to make anyone do it now. I was going to make Robert there do it in front of all of us, but I promised him I wouldn't. Let's say, just to show, let's say you measure B to be B2 to be plus 1 and B3 to be minus 1, and also measure B1 to be plus 1. So B1 is plus 1, B2 is plus 1, and B3 is minus 1. And so that will imply that B1, B2 here are positive, okay, because they're both plus 1. So that will imply, well, in order for this always to be plus 1, A1 has to be minus 1. Right? You with me? I hope so. Okay, A2 has to be minus 1. And A3 has to be... there we go. But you know what? I knew would not be shy. Okay. So, great. It turns out you can convince yourself that if this is true, then it must be, you'll be able to deduce, it must be that if the experimenters had chosen to each measure A, then the product then would always be plus 1. If this is true, then this is true. And that's the homework assignment. I'm not going to go through it with you, but trust me on this one. Okay? So this is always true. If these guys have specific states, then that'll always be true. And this is always true since the measurements at each detector are independent. Namely, the measurement of A here won't depend upon whether you measure A or B here. We're assuming they're completely independent. That's really important. So this experimenter doesn't phone this one and say, did you measure A or B before they measure that one? Okay? Well, that's great. But now I can tell you what's actually happening in this experiment. I'm going to draw things that look like mathematics, but it turns out what's happening is you're sending 3 elementary particles to 3 different detectors. And they're in a quantum state that's called entangled. They're in a superposition of states. It turns out that's the really crazy thing. Particles can be in more than one configuration at the same time. And what we have here is 3 particles, and their spins are all pointing up. But they're also half the time pointing down. It's a superposition, a coherent superposition of 2 states, which can't happen classically, either one or the other. It turns out, so this is pointing in the z-axis, say. 2 nights ago, I would have said the z-axis because I was in Canada, but the z-axis. Okay, A1, it turns out A1 measures the spin in the x direction. Turns out, the neat thing is if a particle is spinning in the z direction and you measure whether it's spinning in that way or that way in the x direction, there's a 50% probability you'll get it spinning that way and a 50% probability you'll get it that way. So A measures the x direction of the spin, B measures the y direction of the spin, and you always get either plus or minus 1, 50% of the time, it turns out. But what you can show is if I send this state to those 3 detectors, that entangled state, each detector measures just 1 particle, but they're entangled. They were set up to be in a specific quantum mechanical state. Then one can prove, and again, this mathematics is a little more complicated, that whenever I measure 1A and 2 Bs, the answer has to be plus 1. That will always be the case. But you can also prove that whenever I measure 3 A's, the answer is always minus 1. There's no example I know of that can demonstrate more clearly than this the fact that quantum mechanics is not sensible. Because if the particles were in some specific state before you measure them, then this is impossible. I think I wrote that down on the next slide, if I can get to the next slide. This is classically possible only if somehow what I measure here will affect the measurement of something over here. You see, if there's some spooky action at a distance, then I get a different answer if I measure A and 2 Bs than if I measure 3 A's. Even though the experiments are independent, if somehow there's a spooky action at a distance, then you can imagine, okay, whenever guy over there measures B, I'm going to measure something different when I measure A here than if that person didn't measure B. That's the only way classically you can understand it. That's why people like Einstein and others talk about spooky action at a distance in quantum mechanics. But it's only because they're thinking about it the wrong way. They're insisting about thinking about the world classically when the world isn't classical. And people write books on this, about this, as I'll show you. So this is Sidney's argument. He said, why do they write long books about quantum mechanics and non-locality, full of funny arrows pointing in different directions? It's because I think, secretly, in their heart of hearts, they believe it's really classical mechanics, that we're really putting something over on them. Deep, deep down, it's really classical mechanics. So you read books about many worlds and spooky action at distance, and I added, I'm less generous than Sidney, and I say there's another reason that people write such books. They want to appear profound. Writing books about many worlds, it sounds really neat. But as Sidney put it, and this is really important, every successful physical theory swallows its predecessors alive. Special relativity and general relativity swallowed Newtonian mechanics. Every new theory swallows the old theories. And in every other area of physics, I don't know why, we know general relativity tells us space is curved. But if we insisted on talking about the universe as if space wasn't curved, then the results we get would be really ridiculous, be strange. Why? Because we're taking a world that we know is not the world and trying to interpret the results in terms of that world. The right thing is not to interpret the world in terms of Newtonian mechanics, but to talk about general relativity. The right way to talk about the world is not in terms of classical mechanics, but in terms of quantum mechanics. So you don't want to interpret the concepts of the old theory. The right way to do it is to understand the concepts of the old theory in terms of the new theory, not to describe the things that happen in the new theory in terms of the old theory. You're always going to result in something that seems absolutely crazy. Okay, and that's getting things asked backwards. So whenever we hear the interpretation of quantum mechanics, in my mind, whenever I hear people talk about interpretation of quantum mechanics, I stop listening. Because that's the wrong thing. What we need to do is understand how our classical world, the world that seems sensible, arises out of a quantum mechanical world, not the other way around. And I think Sidney gave a great, I think this is his example. This is all the standard nonsense collapse of the wave function, many worlds, spooky action distance, all because we insist on treating the whole system or parts of the system classically, instead of understanding that not only is the thing we're observing quantum mechanical, we're quantum mechanical. And once we understand that we're quantum mechanical, everything changes. And I love the example he gave. Many of you may remember, he said, why do we see something definite? Like we always measure the spin of the particle being up or down. We never measure it to be at two places at once or doing two things at once. That's because we, the measurers, are also quantum mechanical. Okay? And he, I don't know if there's a play of Tom Stoppers, and he gave an example. I love this example. A friend is walking down the street in Cambridge and sees Ludwig Wittgenstein standing on a street corner lost in thought and says, "What's bothering you, Ludwig?" And Wittgenstein says, "I was just wondering why people say that it's natural to believe the sun went around the earth rather than the other way around." And the friend says, "Well, that's because it looks like the sun goes around the earth." And Wittgenstein says, "Well, tell me, what would it have looked like if it had been the other way around?" Of course, it'd look exactly the same. And that's the point of quantum mechanics, as Sidney put it. When people say that the reduction of the wave factor collapses occurs because it looks like, they say it happens because it looks like the reduction of the wave factor occurs. And that's true. But what I'm asking you to believe, he said, is to seriously consider what it would look like if it were the other way around. If all that happened was causal evolution according to quantum mechanics. And that's so the weirdness appears to be weird, but if the other way around, it will just be just as weird. If you understand that we are quantum mechanical systems and they are quantum mechanical systems, you'll realize why every measurement we make seems reasonable, while the underlying world is crazy. And I was motivated to include that example of matter for you because I get so frustrated reading all this crap about quantum mechanics, which is probably the most misused area of physics. Misunderstood, and of course it develops all sorts of nonsense like The Secret, which I constantly meet people who read and anyway. But I also read books by physicists about all the weirdness of quantum mechanics, and it is weird, but the key thing, it's only weird if we treat part of the world the way it isn't. If we treat part of the world as classical, when really the whole world is quantum mechanical. And everything we see that seems sensible becomes completely reasonable once you understand that fact, even though the quantum world is itself completely different than anything we'll have ever directly experienced. Okay, we're heading in the home stretch here now, because we now get to life. We leave the domains of cosmology and pure physics. And some people, I remember I was on a boat. Actually, I was on a boat with someone in this room, Bruce, and there were a bunch of biologists, and one of the people came up to me and was very angry and said, "I hate when you physicists talk about biology." Okay, well, the point is, there's a long tradition of that. Anyway, my quote actually is from Jean-Paul Sartre: "Everything has been figured out except how to live." And that's true. The whole point about life comes from Carl Sagan. If you understand the origin of life, you have to understand what he said, the recipe for making an apple pie. If you want to make an apple pie, the first step in the recipe is create a universe. Now that sounds facetious, but when it comes to the origin of life, it's probably incredibly important. Understanding the origin of life on Earth is intimately related to understanding the nature of the universe, as I'll talk about a little bit. And in the question period, maybe more, because I know at least one person here has questions. But there's a long tradition also of physicists thinking about this question. Erwin Schrödinger, the developer of quantum mechanics, one of the developers of quantum mechanics, in 1946, wrote a very significant book, an impactful book called What is Life? This young guy who wanted to be an ornithologist called Jim Watson read the book and said, "You know what? Maybe genetics is more interesting than ornithology." Okay? And he went on with Francis Crick, who, by the way, was a physicist, to discover DNA. And worked with people like Max Delbruck, who won the Nobel Prize in Biology for his work on nature of life while he was still in a physics department, by the way. So I'm not usurping. It's a long tradition of this connection. The universe is the way it is, and it isn't defined by 19th century disciplines. And those disciplines are merging together more and more in the 21st century. But I want to talk a little bit about life. I have a picture here, because if I ask you to define life, it's not so easy. What's alive and what isn't? You might say things are alive. Well, what's life? Maybe life is something that has a metabolism, it uses energy, and it reproduces relatively faithfully. Okay? That's pretty good. But the problem is, if you use that definition, fire is alive. Fire has a metabolism. Forest fires reproduce relatively faithfully, depending upon the kind of trees in the forest that are being fired. The heat will be the same, of course, and not only that, they'll reproduce and grow. And so you have to be a lot more careful. You have to talk about a lot more things when you think about life. And that's important if you're thinking about the key open question, which is the origin of life. The origin of the diversity of life is a question that Darwin answered with natural selection. But the open question that still remains, that all of you ask, is how did life originate? How do we go from chemistry to biology? The open question really at the forefront of much of modern biology. And by the way, it's, as I'll indicate, I think it's a question that's likely to be answered in the lifetime of almost everyone in this room. I think it's one of those known unknowns, one of those bits of edge of knowledge where our picture is changing so rapidly and new experiments are coming online that are going to change everything. But when you think about life, this is a question. You know, the virus, SARS affected all of us. COVID affected all of us. It's a virus. But biologists say viruses aren't alive because they can't reproduce unless they hijack the machinery of your cell, so they're not alive. I refuse to accept that argument. I refuse to accept that I had to wear a mask and stay indoors because of something that isn't alive. As far as I'm concerned, live viruses are alive. And in fact, viruses are important because not only they're probably the reason we're here. They kill you, but they probably help create us. The most important moment, perhaps, in the history of life on Earth happened as Carl Sagan's first wife, Lynn Margulis, demonstrated, when probably a virus, a single-celled molecule, was eaten by a cell, and that virus could do something the cell couldn't do. It could process oxygen and produce energy by processing oxygen. It's what that happened to become was it became a symbiotic relationship. It actually lived inside the cell. We now call it a mitochondria. And the mitochondria are the part of our cells that process oxygen, which is essential for our given life. So viruses of course, have impacts, but they're not all bad. When the viruses get hijacked, or they can hijack a cell's machinery, but sometimes they hijack the cell's machinery to do good things. And for all of us, photosynthesis turned into respiration because of exactly that kind of hijacking. But so we can understand key moments in the history of life by looking at things like mitochondria and the genetics of mitochondria. But there's still a question, and it's a question that actually motivated Schrödinger. It's the question that I still get when I debate. Well, I don't do it anymore. When I used to debate creationists. Okay? It's this famous question. I forget which bishop gave the question. I don't want to dignify him anyway by name. The idea is, they say, well, look, that evolution didn't happen. It couldn't have happened. Because it's like, expecting nature to randomly produce the diversity of life on Earth is like imagining a hurricane blowing through a junkyard and producing a 747. I mean, it just seems impossible. I mean, because the machinery of life is complicated. The first argument, they say, is it violates the law of physics, the second law of thermodynamics. That's why one of the reasons that motivated Schrödinger. The second law of thermodynamics says that the world gets more disordered. Well, that's a very parochial way of describing the second law of thermodynamics. It's not the right way. The second law of thermodynamics says if you have a closed system with no energy going in or out, that system will always over time get more disordered. But life isn't a closed system. If it was, we wouldn't be alive. We're nourished from energy from the sun and donuts and all the stuff you ate before you came in here. That allows a system to retain and increase its complexity, and it's not violating the laws of thermodynamics because it's not a closed system. Closed systems cannot support life. Okay. But nevertheless, even the simplest parts of our genetic code, and this is a ribosome, it's incredibly complex. And it's been a challenge to understand how you can get from simple organic molecules to an ordered system. This may not look ordered, but it tells you how to make proteins that keep you alive. And it turns out, while it violates all common sense, as I've tried to explain to you, the universe doesn't care about common sense. And there have been developments that I don't want to go into because it's late, and I have about 5 or 10 more minutes left to do what I wanted to do. As I've often said on stage, or Richard Dawkins has said on stage with me, our intuition emerged from the savannah in Africa. Okay, it's amazing that we can do what we can do. It certainly didn't give us any sense of understanding long times. That's why evolution seems like such a strange thing to people. We can understand a year or 100 years, but maybe even 1,000 years, but 1,000,000 years or 1,000,000,000 years, just numbers. Okay, and as Richard likes to point out, we didn't evolve to understand quantum mechanics. It's amazing as an interesting side effect of whatever caused it to be genetically or natural selection to prefer objects that have the ability to do mathematics. It's a total side effect, but it's wonderful because we can understand quantum mechanics, but it still means we can't intuitively understand a lot of things. But one thing that chemists are now doing, John, I forget his first name, at Cambridge, has done experiments showing that in extreme environments, like the environments on comets, on Earth, it's natural to take complicated molecules and break them down. That's the direction things go, always. It's left on their own, unless you dump energy into them. But in exotic environments with ultraviolet light and all sorts of things like happen in comets, it turns out you can show certain reactions will work in the other direction. They'll build up complicated things from simple things. In fact, he's been able to build the basis of RNA, showing just simple chemical reactions that could happen on comets. Jack Szostak, who's a Nobel Prize-winning biologist from Harvard, who's turned to the origin of life, has also shown that lots of other non-intuitive things happen. When you cool things down, chemical reactions are supposed to get slower. But you can show when it comes to building complex chains of organic molecules, polymers, that actually when you cool them down, and I'm happy to talk about this in the question period, certain reactions can happen that would never happen at room temperature. Again, comets are great places for that. That's why when we look at comets, we see amino acids. We see many amino acids. We see the basis of the organic materials that cause life to form. And I'm expecting, I would not be surprised within the next decade or two that someone comes up with a clear chemical pathway that naturally, without any anything external except energy from the sun and water, allows chemistry to turn to at least the basis of RNA, which is what we think was the first world. The RNA world preceded the DNA world. But the other thing is that the way we really may learn about the origin of life is not by looking at life on Earth. The problem of the universe is we have one example of life. And the other area that's changing dramatically is the realization that we may soon be able to observationally find out if we're not alone. Now, what we'll find out is we may share the universe with microbes, but that's a big step. And there are many developments recently that have changed that. One, if you're as old as I am, and you remember Bill Clinton in the White House in 1996, I don't know if you remember this, he made a huge announcement that we had discovered evidence for life on Mars. Because people saw a Martian meteorite, which they'd gotten from the Allen Hills in Antarctica, which is where we find meteorites when we look for them. Why do we look for meteorites in Antarctica? Let's just try and wake some of you up again before the end of this. It's white. That's right. So it's easy. I actually applied to do this because you don't need any skills. You just get a snowmobile and you drive along the ice in Antarctica, you see a rock, it's from up there. And so a rock was discovered that had the same composition as other Martian, we'd sent rovers and other things up to Mars, and we know the composition of the soil there. But inside, when it was dissected by some chemists from Stanford, there were these things that looked just like the first fossils of life on Earth. And they thought this is evidence of extinct life, because Mars was once hotter and wetter, okay? And in fact, my friend Andy Knoll has said that, who's on rover missions, has said that he would be surprised if we discovered any extant or extinct life on Mars if it wasn't our cousins. Because what that rock showed us, and what we now know from microbes and extremophiles, is that a rock knocked out of Mars by a comet or something that hits the Martian surface that makes its way to Earth, if microbes existed, they could still exist. All the way, they could survive in an inert state. And so it could be, if you wonder what Martians look like, look in the mirror. It could be that life first originated on Mars and then came to Earth. You don't know. But that's really important. It's taught us that we have to be careful when we look for life. If we discover life on Mars, it may not be an independent genesis of life. Running water on Mars, we've now seen, and that means we know the environment on Mars was particularly susceptible. But the really interesting places are not Mars. They're like the moons of Jupiter and Saturn, Enceladus and Io, because those are ice moons with kilometer-thick layers of ice surrounding an ocean, a salty ocean perhaps. Underneath, we see plumes of water coming out from those oceans because some of our satellites our spacecraft have traveled through them, and we see organic materials. There is a NASA mission proposed in, I think, 2030 something, to go to Enceladus and drill underneath the ice. If we discover microbes of any sort, life like we know it or not like we know it, in the ice in Enceladus, it'll be almost certainly an independent genesis, because that air region has been closed from the rest of the solar system. And so we are living in exciting times. We may discover, if we discover 2 independent geneses of life on Earth, then it means that the galaxy, which has 100 billion stars, and we've now learned, as I'll show you in a second, that almost all stars have planets around them, 100 billion solar systems, life could be ubiquitous. And of course, JWST is the next stage. It's going to look for that, and I just want to show you an image. Here's what we're going to see when we look at other planets. In certain cases, we're lucky enough to see a planet orbiting its star with a planet goes in front of the star, causing the star to dim a little bit. Not a lot, 1% or less. Actually, when it goes behind the star, it actually makes the star, this isn't quite right, when it goes behind the star, it actually makes it brighter because it's reflecting the light from the star as well. But in any case, when that happens, that's neat, and that's the way we've discovered extrasolar planets, 4,000 of them so far. But more interestingly, when it goes in front of the star, if it has an atmosphere, the light from the star goes through the atmosphere. And then we can look at the spectra of that light. And if the atmosphere has certain elements, we can see them. Here's a measurement of the atmosphere of a specific planet whose there we go, gas giant exoplanet WASP 96b. Okay, we've already been able to measure water in that atmosphere, but maybe we could look for other biomarkers like oxygen. There was no free oxygen on Earth when Earth formed happily, otherwise we wouldn't be here. If we saw an oxygen atmosphere, it wouldn't be proof that life happened, but maybe we'd see methane too. And so you could see, we may, in the coming decade, be able to have definitive evidence of whether there's life elsewhere in the universe, microbial life. Whether there's intelligent life is a vastly different question, and the answer to whether there's intelligence elsewhere in the universe is, we don't know. We're looking, but it's a long shot. But our whole picture is changing. The last topic, you'll be pleased to know, that I wanted to go into is consciousness. Some of you have lost it, I can tell already. It's the most complicated subject of all. And actually, the most interesting quote about consciousness came from the physicist Erwin Schrödinger. I think it's one of the reasons why consciousness is so hard to understand. Consciousness is a singular of which the plural is unknown. And that's the hard part about studying consciousness. Most of us are conscious. There are notable people I could mention that probably aren't, but I won't. But we don't know, when it comes to other species, whether they're conscious. It's even hard for us to know whether your consciousness, I don't know for certain that your consciousness is the same as mine. How do I know that? All of these things make understanding consciousness very difficult. And in fact, if defining life was difficult, consciousness is much harder. What I discovered in my work when I tried to update my knowledge of the subject, I spent a lot of time before talking to people, was that most cognitive scientists actually don't define consciousness. It's too hard to define because we don't really know what it is. What they can do is look for differences in human neurobiology compared to other organisms and look for how those differences might have evolved evolutionarily and try and pick out what may make us special, if we are special. But unlike legs or fins, we can look at fossils, we can measure legs and fins, but we can't look at the fossils and measure consciousness. We can't even look at other animals and unambiguously say whether they're conscious. In extant species and species around now, there are debates about levels of consciousness. I'm convinced my dog is conscious of me. But it's not. But there are a lot of people who argue I'm just anthropomorphizing when my dog appears to be sad or happy. And it's extremely difficult. Well, it turns out to be even worse because what we can do is probe behavior, but that doesn't tell us anything. Too many people associate behavior with consciousness. And a really good example of why that's a bad idea comes from single-celled animals. Protozoa can swim away from harmful environments, and even bacteria give some behavioral evidence of learning and memory. They don't even have neurons. So clearly, the behavior that they have to avoid danger is not consciousness. And if that behavior suggests to us as consciousness in bacteria or maybe animals, we've got to be very wary about us assuming that. And in fact, Bertrand Russell said, I think somewhat facetiously, but nevertheless, from the protozoa to man, there is nowhere a very wide gap, either in structure or behavior. I think the events of the world in life and time suggests that there may not be much difference between humans and anything else. In our own species, and this is, the last thing I want to do is show you an experiment, one of the neatest experiments in consciousness that I know of from Michael Gazzaniga at UCSB. We don't even understand our own you have a consciousness and you're lying to yourself all the time. David Hume was right when he said reason is a slave of passion. And the experiment that I want to talk to you about is an amazing experiment, a lovely one. Just a little bit about the brain. The brain has two halves, the left hemisphere and the right hemisphere, connected by a thing called the corpus callosum. Women have larger corpus callosums than men, which is why my wife tells me that women can multitask better than men. I don't know if that's the case. But let's see. Your left body motor control is controlled by the right hemisphere. Right body motor control is controlled by the left hemisphere. Similarly, your left visual field is controlled by the right hemisphere of your brain. The right visual field is controlled by the left hemisphere of your brain, but speech processing is completely within the left hemisphere of the brain. What happened? Well, it turns out epileptics, it was discovered that if you sever the corpus callosum connecting the left and right hemisphere, then for some epileptics, you'll reduce the effect of seizures. So it was done. But what Michael and Gazzaniga and others said, these are great test cases, because these are individuals where the two halves of the brain don't talk to each other. Let's do some experiments. And this is an amazing experiment. So they put observers sitting on a table where there was a barrier, so the left eye could see one thing and the right eye could see another. And in the left visual field, they put a scene of snow. In the right hemisphere, they put a chicken. Now, there was a box, and they allowed the people observing with their left hand to pick something from the box that was characteristic of the field they were seeing, the right box, okay? So remember, the left and visual field and the right visual field are also controlled in the same hemisphere with motor control. So they were able to do that, and what happened was the observers would pick a snow shovel, because they were seeing a snow scene, and they'd pick a chicken on the right hemisphere. All good. But then they asked those people, why did you pick that? But it's only the left hemisphere that controls speech. And the left hemisphere can't see the snow scene. Okay? Because that's the right hemisphere that observes the left hemisphere. So when they did that, what the people said was the chicken claw goes with the chicken, and you need a shovel to clean out the chicken shed. So the observers, there's nothing unusual in them. They knew why they were doing what they were doing. But that's not why they were doing it. Our conscious awareness of ourselves and what we're doing is an illusion. And we have to understand that's why it makes it so hard to understand consciousness. Okay, that's what I already said. They made a narrative that made sense to them, to the left hemisphere. And we do that all the time. Our sense of self, philosophers often say, is an illusion. Again, just like time, to revert to the beginning, saying our sense of self is an illusion means nothing to me. The question is, how does that illusion arise? And that's what we're trying to understand. And just like time being an illusion doesn't matter to you if you're late for a job. If you get kicked in the shin or jilted by your lover, telling you that your sense of self is an illusion is not really comforting. And the key question is what ultimately produces that, and we don't know. And I think the way we may know may become just like understanding life may require us to look elsewhere in the universe. Understanding consciousness may require us to create consciousness. Richard Feynman once told me, the way he put it to me is, he who can do nothing knows nothing. But on his blackboard, after he died, there were a few things he wrote on the blackboard. And he said, if you can't build it, you don't understand it. Maybe the way we'll understand consciousness is by building conscious things. ChatGPT 5 isn't conscious. Maybe ChatGPT 50 is. I doubt it, by the way. But and I doubt quantum computers will necessarily produce that, but they might. But interestingly enough, that may be the way we learn about how consciousness arises. But people are worried about what happens when you open the genie, take it out of the box. And there's huge debates. And in fact, a future podcast that we just recorded for the Origins podcast is with the computer scientist Scott Aronson, who's involved in trying to understand how to make sure AI systems don't misbehave. It's a fascinating challenge. But I just want to point out I'm not the pessimist that in this regard that other people are. And my object lesson is history. In the 9th century BC, and by the way, this is the last thing I'm talking about, just in case you're waiting. The derivation of the Phoenician alphabet was introduced into Greece and evolved in a few hundred years. It happened in the 9th century BC. What was the response of intellectuals? It was viewed as the end of literature and drama. Being able to write was going to kill storytelling. Plato said, writing was an impediment to wisdom. It did not capture the whole truth. It propagated the illusion of knowledge and would eliminate the need for memory. Because if you could write it down, you wouldn't have to remember stories, and remembering stories was so important. Socrates was quoted as saying something similar. He was suspicious of writing. He argued that written communication would never be as clear as face-to-face communication because we couldn't ask questions of a document. Intriguing, rather prescient, actually. AI is like writing. It's a natural byproduct of human intellect. ChatGPT writes, but it's a natural product. And it's going to change what it means to be human. But every single invention we've ever made changes what it needs to be human. And it doesn't have to be at worse. I mean, we don't live the way we lived before we had smartphones. Our whole life is different. Some people think it's better, some people think it's worse. On the whole, I think most people think it's better, but that's a question of debate. It's nothing new. I believe, since I write books, that a world of books is better than a world without books. It made the world better. It made it different, but it didn't make it worse. And an AI future could be better than the present or worse. It's up to us. Louis Pasteur said, fortune favors the prepared mind. In a book before this one, I wrote that the future is charging towards us like a freight train, but it's doing so on tracks that we have built. We get to think about this, but we don't always have to assume it's going to be worse just because the future is going to be different. And just because it's going to be different to be a human being doesn't make it worse. In fact, it can be better. Max Planck said, physics progresses one funeral at a time. And the beginning of science and the first step on the road of wisdom to think about the future and to recognize that we don't know what's going to happen. Humility and honesty demand that we be clear about the limitations of our knowledge. That's the thing I want to get across, and all of you appreciate, but too many people don't. We shouldn't be shy about this. We should celebrate it. And I would celebrate it. I hope I've shown you just a taste of the remarkable mysteries of the world that are now present. They are, by the way, and I only realized after I wrote the book, exactly the same questions you all ask about the universe anyway, are the same questions of interest to physicists at the forefront. Are we alone? How did the universe originate? How did life originate? When I see green, is it the same thing as you see green? Those are the same questions that are driving science. And the three most important words in science are, I don't know. And I'll leave with two quotes from Einstein. The fairest thing we can experience is the mysterious. It's the fundamental motion that stands at the cradle of true art and true science. And the Origins audiences appreciate that. Too many other people are afraid of the mysterious. But the mysterious is an invitation to discover. And that's what makes life worth living. But to discover it, the last thing Einstein said, which I think is very important, is we cannot solve problems with the same thinking we used when we created them. And that's the most important lesson. To understand what we don't know means that we may have to develop new ways of thinking, and that's true not just in science, but as is obvious this week in politics and in world affairs. And to have that mentality requires you to understand that you don't know everything and be excited about that, as all of you are. So I think it's time for a break. Thank you. Good hour, 15. Okay, good. Well, thanks again for the questions and for your indulgence and for being here. It really is a pleasure, and it's always so humbling for me to see that people are interested. Okay, Skylar said, in your lecture you mentioned time travel to the past through wormholes. Let's say the theory was correct. Say you did arrive a year in the past from which you left. Would you then have entered into an alternative reality in which there is a reality moving a year ahead without you, while simultaneously you are altering the past, which has now become your present? The answer is, I don't know. See, a lot of these have a simple answer. Victor asks maybe a more serious question. Well, that was a serious question. It's just, I don't know. But to be less facetious, some people have argued that that's a way around the paradoxes of time travel, that when you go in the past, you don't come back to the same present. Some people have argued that somehow you're entering a different branch of the quantum wave function, but those are the same people who write books about many universes, those are the people who like to mystify quantum mechanics, but I don't think that makes sense. But it could be that you do change reality. And in fact, well, anyway, the strangest thing of all is that quantum gravity, as I'll talk about with some of the questions, space and time are intimately tied together. But if you want to discuss the quantum mechanics of the whole universe, you understand all of space, but all of time. So it could be that all of time already exists, and the present is, that the present is just a part. So the future is already determined and has already happened as much as the past. All these things are fascinating, but we don't understand any of it. Victor says, how as a society can we overcome the resistance to change our minds in the presence of evidence? I really wish I knew the answer to that question. I try in my own way, and we try at the Origins Project to do just that, to show people that you can change your mind and it's a good thing, and evidence is the way to do that. I've said this before, but I'll say it again, that I've been a teacher for much of my life, and so there's an old saying that if the only tool you have is a hammer, everything looks like a nail. And I do think the only solution is education. But we have to change the way we educate people in the modern world. Most of us grew up in a time of education where you learned facts, and that was what school was for. And that's the least important thing, except for the basics of how to read and write and do mathematics. But beyond that, facts are largely irrelevant, because there are more facts in my phone than I will ever know. There are more misfacts. And so what we do, in order to get to that future that you're talking about, I think we have to change the way we teach students by getting them to understand critical thinking. The real reason science is important is not just that it's changed the world, made it better, and revealed mysteries beyond our imagination, but it's because science works. The scientific process should be applied, should be useful to the rest of our lives. Constantly skeptically questioning, testing, retesting, those are the kind of things we should teach. So science shouldn't be a set of facts. Or biology, when I kid was dissecting a frog and memorizing the parts of a frog, one of the reasons I didn't become a doctor, as it turns out. But we need to, instead of doing that, we need to get people critically examining the universe, and that means teaching through questioning, asking questions, not knowing always the answers, exploring the unknown that way. I was in a movie once called, I forget the name of it now. It was about the Voyager satellite. It was a great movie made by an Irish director, and I was in Ireland when it opened, and it hit me then that something that I suppose should have hit me years before is that when every time a young person learns something, for them it's the first time in the history of the world that that's been understood. And so instead of teaching kids as this is what we know, we should teach them that voyage of discovery. And that voyage of discovery is seductive. Once you start learning that way, once you see the world as being a series of discoveries and how to make those discoveries, then it becomes innate. And I think that's the only way we'll get beyond our current state. And that means educating and changing the way we educate. But it doesn't just have to happen in schools. Parents have to be willing to say, I don't know, let's find out. And it's a long, slow process. And I don't know if it'll ever happen. I often, in my book, The Physics of Star Trek, I think I said the most realistic thing about the Star Trek future was that everyone was scientific compared to the world we lived in, even the therapists. Anyway, so it'd be great if we had such a future. That's why I like Star Trek, by the way, because it presents a not dystopic future. It presents a future where science can actually make the world, as it has, in my opinion, a better place. But it can really impact and change society in a more rational way. And my goodness, if there's ever a time when we need rationality, it's the current time, and I'm just incredibly depressed about that. Could space and time exist separately by themselves? And if so, how could that be explained? The answer is not really. And I didn't emphasize it enough, but space and time are tied together in relativity in a real way, because the reason they form a four-dimensional universe of space-time is that one person's space is another person's time. And the analogy is a three-dimensional universe, okay, or a two-dimensional universe, in fact, where I could have the y direction and the x direction, okay? And I have things that happen in the y direction, things that happen in the x direction, okay? But I can do a rotation. And now what was once the y direction is now partly the x direction, and what was the x direction now partly the y direction. That's why you learn trigonometry in school. We understand how that happens. What Einstein showed is that when I'm moving with respect to you, in a sense which is a little bit more mathematically complicated, but essentially the same thing, there's a rotation, so that what was my space becomes a little bit of time. In fact, one of the questions from Raphael, in fact, I think, is why does the train get smaller when we observe it to move? Is exactly that. That's why I put it next to this question, because what happens is, think about it. If what really matters is the four-dimensional length of a train, the three-dimensional length is just a projection. Just like this card, okay? It's at a certain length. You can look at it. But if I turn it that way, it's less long for you if you're looking straight on, right? But we know that's just an illusion because it's rotated in the y direction. It's less long in the x direction, but it's rotated. We understand there's a fundamental length that doesn't change. In special relativity, there's a four-dimensional length that doesn't change. And the three-dimensional length we measure is a projection onto space of that four-dimensional length. So when a train is moving, it looks shorter. The three-dimensional length is shorter, but remember I told you it's now spread out in time. Because now the front of the train and the back of the train are different times. So it's got shorter in space, but it's spread out in time. And the four-dimensional length remains exactly constant. It wasn't Einstein who realized that, it was his professor, Minkowski. And we call that Minkowski space. So not only can space and time not be thought of as being separate, because just like we can't think of the x and y directions separate in a world in which we can make rotations, we can't think of space and time as separate in a world in which we can move. And it's that four-dimensional space that is invariant, that never changes, but the three-dimensional space and the one dimension of time change in a slightly more mathematically complex version of a rotation. And we're like those two-dimensional beings who try to imagine a three-dimensional universe. It's hard. And when I look at you, I'm taking a slice, but it's really an illusion, because when I take a picture, which I'm going to do because I meant to do that, I'll take a picture of all of you because I like this. There we go. Smile. Don't move. Okay. And my favorite Woody Allen joke about that is why was the picture of the Earth blurry when I took it from space? Because someone moved. Anyway, but when I take a picture of you, I have the illusion that I'm taking it right now, right? But it's not right now, because the light for the people in the back of the room took longer to get to me than the light for the people in the front of the room. So I'm taking my picture is really spread out in time, but I have the illusion that it's an incident. And it's because the speed of light travels so fast that this that this separation of space and time appear to be the case. But if it was much slower, then it would be obvious. Okay, anyway, that's my little digression. I took this question because it represents a common misconception. Does the fabric of space cause a massive object, a star, a planet, a black hole, etc., to push down in a certain direction for an outside body to fall towards it? On Earth, the trampoline example shows this. Every science museum you go to has an example of you push down on a bed sheet and a coin will go in a circle around that, and that's the analogy of the curved space. But the problem is it's like all analogies, only an analogy. The real universe is three-dimensional, and there's no sense in which an object pushes down on anything. It just curves space around it. It is true that light travels in straight lines in a curved space, and light will therefore bend around the Earth a little bit around the Earth, more around a black hole, as you saw from the pictures of the black hole. It can go in a complete circle, but it's not pushing down on anything. That analogy is unfortunately not a good one. In fact, it's even a worse analogy because you're using the gravity of the Earth to make it work, right? Push down on the trampoline, and the reason the coin falls down is because the Earth is pulling it, not because of the curvature. If you did the experiment in space, the coin would just keep going because there's no gravity. So it's a nice little bit of analogy, but it leads to a misconception. And this is the misconception. So there's no sense in which objects push down. They just curve space around them. Kyle asks, given that we can even describe consciousness, do you think a computer can become conscious? Is the substrate for consciousness biological, or is it information? Well, of course, the answer is I don't know. But I think it's, if you ask me what I suspect, which is there's nothing, biology I don't think is an essential part of consciousness. Consciousness is a property of certain biological systems. How many, we don't know. I'm a vegetarian because I don't know the answer to that question. Okay? Honestly, that's one of the reasons I'm a vegetarian. But I see no fundamental, since biology is just chemistry and chemistry is just physics. There's nothing special about biological systems that I can see, and therefore I see no reason why a non-biological system could not become conscious. As I describe in the book, in ways I wasn't able to talk about in the lecture, I think they're really good arguments by a number of neuroscientists, one in particular, actually from San Diego, that one of the central features of our ability to become conscious is our ability to sense the outside world, which is required by what's called homeostasis. One of the properties of life that makes it different than fire is that a fire is uncontrolled. Living systems are highly controlled. It's really important that the chemistry of burning in our bodies, because living is just controlled, burning isn't uncontrolled. If those reactions could happen without enzymes, then all of the materials on the Earth would already be oxidized. Enzymes are needed to make reactions happen so we can control them, so we can heat up or cool down or do whatever is necessary. And as a complicated system gets more complicated, the machinery that controls the homeostasis of that system needs to become more complex, suggesting the building of a nervous system, which can probe not just the outside world, but the internal configuration that you're in. And so it's been argued by this person, and I think it might be that, AI, GPT-50 isn't going to become conscious because you have to have nerve endings. You have to be able to probe the outside world and ultimately have feelings. That's what nerves lead to, is feelings, first feelings of pain and pleasure that ultimately lead to feelings that are conscious feelings. This is an argument that seems plausible to me, but ultimately, I don't see any of those things as requiring biology. I think it's pretty inevitable, if things continue, that it's likely that the dominant form of intelligence on the Earth will become non-biological. But that does not bother me. Bruce asks a similar question, which is, what biological factors determine levels of consciousness, i.e. consciousness of the universe versus consciousness of a tree, humans versus dogs, okay? Um, although my first wife used to say men are dogs. But anyway, uh, uh, the that's a good question. I think, of course, the answer is we don't know. But one of the ways we can look at that, and I talk about it at length in the book, is looking at the evolutionary structures of the human brain versus the evolutionary structures of other mammals. And in the prefrontal cortex, you can see a whole new kinds of cells, layers of cells in the way they're put together that are not present in dogs. And in fact, not present, the number of things not even present in our nearest primate cousins. So I think the way we could try and ultimately understand that is if we understand how those different level of cell connections in the prefrontal cortex and elsewhere contribute to consciousness. But that's such a long way away, and it may be the wrong question. It may ultimately even be the wrong question. So, but it's right now, in my opinion, the best way that scientists can try and understand consciousness is using exactly that kind of evolutionary tactic. What's different, not about behavior, but what's different about the way the brain is, the neurobiology, human brain is versus that of dogs. And so we don't share much with dogs, I should say. We share more with birds and other primates when it comes to the ideas of many aspects of what you might argue is consciousness or suffering. But that doesn't mean dogs don't suffer, and my dog certainly does, apparently, at least to me. Anyway, so I think that's the best way to get to it. Elsa asks, why is lithium so important in the atmosphere? Well, lithium is important to maybe some people in this room too. I'm not sure, but it's not really important in the atmosphere. Actually, it turns out it's a trace element. It's important because it's useful for batteries now, and it's becoming more important. And I remember when I was in a movie that was filmed in Bolivia once on the salt flats of Bolivia, and about 30% of the world's lithium, I think, is there because that's, lithium, like sodium, makes salts, and lithium is because of, like sodium, of its position on the periodic table, it is a very good basis for making batteries. So lithium, I don't think, was important in an atmospheric sense. It's barely a part of our atmosphere at all. I'm not sure it's even in the atmosphere, but it's being important. Like rare earth elements like lithium are becoming more and more important for human technology to make batteries and the like. And that's certainly an important consideration. We talk about climate change and say how much of a climate footprint electric cars have. When you consider you need to do a whole new types of mining and factories to develop lithium and other rare earth elements. All those questions are interesting questions. My understanding, by the way, is even after including the mining, electric cars still have less of a carbon footprint. In any case, so that's what I have to say about lithium. Michael asks, what is more mysterious to you, quantum mechanics or human behavior? Well, the answer is obvious to me, human behavior. Yeah, because it seems to have no rules. I know the rules of quantum mechanics, but human behavior is remarkably mysterious, which makes it, by the way, interesting to be human. It's not all bad. I think the fact that humans are not just rational beings is an important part of who we are and what makes it exciting to be alive and terrifying at the same time. If scientists prove life is present on other planets, how do they convince religious authorities? That's a really good. That's a good question, and the answer is I don't think it'll take any convincing, because the great thing about religious people is they know the answers before you ask the questions. And so, when the life is discovered, if intelligent life is discovered on other planets, they'll say, "I told you so." The interpretation of religious texts, which is infinitely malleable, will be malleable. It won't. Many people thought, great, we'll discover other living beings elsewhere, and they'll have a different, they'll have no religion. They'll have different. I think that's highly unlikely. All that'll happen is that religious people their beliefs will morph to encounter that new evidence, because evidence is irrelevant for true believers. I think that's emotionally charged enough for this. in black holes, which I didn't talk about here, but I do talk a lot in the book, time and space flip beyond the event horizon. What might that mean? And the black holes become like elementary particles in some way. Well, there's a lot to unpack there. But what is interesting is that as you approach a black hole, because of the effect of relativity, clocks slow down as seen by distant observers. When you fall into a black hole, your clocks get slower and slower and slower if I'm watching you. And in fact, they freeze on what's called the event horizon of a black hole, which is why in Russian, black holes are called frozen stars, which is a much less sexy name, which is why there are no Russian movies about black holes, as far as I know. But what it really means is kind of fascinating, because it means you never really see anything fall into a black hole, because time for you appears to stop. If you're falling into a black hole, you don't notice that. Okay, you don't. In the event, there's no signpost saying event horizon. If you fall through, if it's a big enough black hole, you're not even crushed when you fall through the event horizon. If it's a big enough black hole, but what is interesting is space becomes time-like and time becomes space-like. Space becomes time-like because time, as far as we can tell, has only one direction, towards the future. That's why it's so weird. When you fall into a black hole, no matter what you do, you put your foot on the gas to try and get out, and you always go in the same direction, towards the singularity of the black hole. Space becomes unidirectional in the sense of time. And whereas time becomes more space-like, because it turns out if you look up, you see the whole future of the universe. If you look down, you see the whole past, in a sense. And so it seems time becomes space-like. If you describe things in those terms, the space inside of black hole can be arbitrarily big, because time is now space-like. So what seems like space can be arbitrarily big, even though a black hole is from the outside really small. From the inside, it can seem really big, like the cabinets in Lion the Witch and the Wardrobe and that sort of thing. It's very strange. You can show this using things that are called Penrose diagrams, which I had a slide to show, but I thought I was going to go long enough as it was, so I didn't. But what happens to time and space inside a black hole are strange but understandable. But what really is not understandable is what happens at the singularity, at the center. There, time and space both seem to end, and we don't understand that at all. I just did a podcast recorded, which will appear sometime, with Carlo Rovelli, who's written a book about white holes, and I think he's completely wrong, I should say that now, but I talked to him about it. But he thinks there's a way that quantum mechanics can resolve this question of the singularity at a black hole at the end of time. I don't buy it, but you can listen to our discussion. Curtis Davidson asks, can you briefly explain NASA's Euclid mission? What experiments will it perform, and what might we discover about dark matter, dark energy? The first thing about it is it isn't NASA. It's the European Space Agency, which is making it, because NASA is wasting a lot of time and effort and money on human space exploration, while other places try to do science. In case my views are not clear on that regard. But NASA collaborates with, but it's actually an ESA mission. It will be launched at Cape Canaveral on a SpaceX plane, or rocket. But anyway, it's a mission just to map in an extremely detailed way the nature of matter in the universe, the distribution of matter in the universe, going as far back as we can see. And by looking at that distribution of matter in the universe, you can try and understand the evolution of the universe from early times to late times better, because the farther away we look, the earlier times we're looking at. And dark matter and dark energy can, depending upon their properties, can change the way the universe evolves. And so if we can very carefully look at the evolution of structure in the universe, we might get a better handle on the nature of dark matter and dark energy. I'm skeptical, by the way. I doubt, I really don't think we'll get much information about dark energy. That's my bet. But you never know until you look. Someone asked, can quantum superposition, be a matter of perspective? For example, if I look at a clock, the dial moves clockwise, but if I'm behind the clock, the dial moves counterclockwise. Therefore, the dial moves both clockwise and counterclockwise. No. I mean, it's a nice analogy, but the thing I'm trying to convince you is there's no classical analogy that works for quantum mechanics. Superposition is not classical because it means that things can, all it really means is that objects can interfere with each other in ways that are impossible classically. Really, that's how a quantum computer works, as Scott Aronson talks about in the podcast that's going to come up. It's not, we often say quantum mechanics allows the system to do many things at the same time, and that's why quantum computers are going to be so neat, because they can do many calculations at the same time. It's actually not that way. It's just that complicated quantum mechanical systems are doing different things, but while they're doing different things, they can interfere with what they're doing in other ways. And you can set things up so that everything, all the different possibilities will cancel out exactly except for one possibility, which will give you the right answer. That's how quantum computers work. But in any case, any classical picture of superposition never can capture this weird fact that you get, that it's really due to something called imaginary numbers. It's due to the fact that probability amplitudes can interfere to produce probabilities. We see the world in terms of probabilities between 0 and 1. But in quantum mechanics, probability amplitudes can be negative and even imaginary. And only after the fact they combine to produce probabilities that are sensible, possible. So it's a long digression, but while your effort to understand superposition is laudable, it can never be right because it's a classical picture. That's what I tried to indicate. One said, can one use the change in time from time dilation of a probe going to the sun to determine if there's dark matter surrounding the sun? And it's an interesting question. The answer is probably not, because there are other ways you could probe for dark matter much more easily. In fact, you can use Newton. You don't have to use Einstein. And in fact, I early on wrote a paper about this. And Newton says that every object attracts other objects, and the strength of the gravitational attraction goes as 1 over the square of the distance between the objects. That brings back happy memories from high school physics for most of you. For none of you, I suspect. Okay, 1 over r squared. But you see, if there's matter around the sun, then it won't be 1 over r squared, because the mass will change. Newton says the force of gravity goes as the product of the mass of the two objects divided by the square of the distance between them. But if there's dark matter around the sun, then the effective mass attracting me further away will be larger than it was if I'm inside that mass, okay? And so if I could look for variations of 1 over r squared, I could search for dark matter. And a long time ago, I did a calculation and others showing that unfortunately, given the kind of dark matter we think there is, that there'd be so little of it that you'd have to be able to measure the strength of gravity and its behavior to better than 1 part in a billion. But it turns out gravity is the worst measured force in nature because it's so weak. So it's beyond our ability to do that right now. But if we were going to do it, it'd be much easier to do it that way than look for time dilation. A musician asks about AI, and basically, how do I feel about the representation of art and music with AI? Will AI be able to create valid works or simply use current examples to guess what an art, how they modify things? I suspect that while it's clear that AI systems are not good at that right now, although they can do certain kinds of art, I suspect ultimately to be I don't see an ultimate barrier to AI producing good music and good art, because it's ultimately making new connections with known things, and I ultimately think that will be possible. I don't see. So and that's scary. But why is it scary? I mean, it's just like AI, I think, or at least quantum computers will teach us things about quantum mechanics that we don't understand now. That's great. That's not bad. It's not bad that a quantum computer will understand quantum mechanics better than we do. What's great is that we can create a quantum computer to do that. And so, it's okay. We already I'm old enough to remember when Bob Dylan first picked up an electric guitar and the fact that people hated him for it, but it's just a new way of creating music. Anyway. Can you discuss your proposal with Frank Wilczek to detect the multiverse? Thank you for asking that question. The answer is basically, it turns out what we showed was that if we can measure gravitational waves from the beginning of time, from this period of inflation, it can do two things. It can prove that gravity is a quantum theory, because there will be no gravitational waves from inflation if gravity isn't a quantum theory. And that's an open question. Some people think maybe the reason we can't unify gravity and quantum mechanics is that at small scales, gravity isn't governed by quantum mechanics. So if we could measure those things, we would prove that gravity is a quantum theory. But also, we could probe inflation. And if we could probe inflation and find out the fundamental physics model of inflation, then we would be able to prove mathematically whether that inflation is continuing to go on or not. And so we could probe the model of inflation that produced our universe, and by understanding that model, we'd know whether it implied the existence of other universes. So I think that's the only hope right now for probing inflation, is to find gravitational waves. I spent a lot of my life early on in that research area, suggesting that we do that. And we're probably a factor of only 1 million away from being able to do that. That may sound daunting, but experimentalists, as I like to say, experimentalists aren't as dumb as they look. They're amazing people, and they can do. I never thought, I didn't talk about LIGO here, but what we can do is just constantly amazes me. And the older I am, the more, in some sense, I'm sad that I didn't. Well, not sad. I look with wistfulness on experimentalists. As a theorist, I'm just amazed at what could be done. And it's really good. Vinod asks, is the Big Bang Theory dead? I'm really glad you asked that, Vinod, because that's what you hear in the newspapers. And what you should always do when you read about science in the newspapers, as well as politics and foreign affairs and everything else, is be skeptical. And the Big Bang is not dead. It's alive and well. There are always open questions at the edge of knowledge. Every time we look at the edge of what we can see, we often find inconsistencies. Most often, those inconsistencies come from the fact that you're not quite sure what you're measuring, and the experiments are hard. And so one of the things that people say that causes the Big Bang, one of them is that we're seeing more galaxies at earlier times than we thought we would in the standard model of cosmology, models I helped build. But it's a complex process. And I have known, for example, I've seen dark matter be killed probably 5 times while I've been a physicist. That's one of the reasons I believe it, because, it gets resurrected. And of course, we all believe things that get resurrected. But I've seen this. If dark matter exists, this can happen. And then, of course, we realized we just didn't understand things enough. Numerical simulations teach us that we really were thinking about it wrong. But the other thing is systematic uncertainties. Systematic uncertainties are, in experiments, we can twist dials and we can look for biases in our experiments. But when you're doing an observation, you can't twist the dial in the universe. And I'm old. And I remember, so one of the things that is also supposed to be killing the Big Bang is that one way of measuring the expansion rate of the universe gives a number 69 plus or minus 1, and another gives 72 plus or minus 1. So they're 2 or 3 sigma apart. Okay, holy mackerel, the Big Bang is dead. Okay, when I was a junior professor, there were 2 measurements of the rate expansion of the universe. One was 100. It doesn't matter what the units are. 100 plus or minus 5, and one was 42 plus or minus 5. I like the 42 for obvious reasons, but if you've read Douglas Adams, but it was obvious at the time that the observer's error bars were too small, right? It was obvious because 100 and so what many of us, I remember saying, The answer has to be 75. It's got to be in the middle between them. What's the answer? It's close to 75. So I'm suspicious of people claiming that a 2 sigma uncertainty in a hard measurement it demonstrates something. It could be right, but there's no observation. The Big Bang really happened. The details of our understanding of the formation of structure may change, and maybe even our details of the understanding of the nature of dark energy may change. I'd love it. I'd love to be wrong. That would be great. But these articles are ridiculous. Oh yeah, last question. I got through them. Well, last question I took, there's 3 or 4 more out back, but they're too technical, I decided. Do we really know what we think we know? Only by questioning the prevailing paradigm can we have the next breakthrough. And I think, of course, the answer is, once again, not only do I not know, but I know I don't know, that I know we need to question existing paradigms. But the one thing that I really want to emphasize is not knowing doesn't mean we know nothing. That's where people get wrong. They say, oh, science can't explain the origin of life. There must be, in fact, I thought I had that intelligent design question. Oh, yeah, I do. I'll answer that one here too. I skipped it. But so you'll say we don't understand how life evolved, therefore it had to have been created by God. It's always because you don't understand something. But not understanding doesn't mean you don't understand anything. What has satisfied the test of experiment will always be true. Newton will always explain correctly the motion of baseballs and cannonballs and even rockets around the Earth, okay, to first approximation. Sure, it's been subsumed by general relativity, but in the domain in which it was meant to apply, it applies. And 1 billion years from now, if we have a quantum theory of gravity, if I take a ball and drop it, it's not going to fall up. So the biggest misconception people have about science is because we don't know everything, we know nothing. And that's not true. We know an incredible amount. There's just a lot more we don't know, which is what makes life interesting. And the last question I then will answer is, because I forgot it, is can you please comment on the theory of intelligent design of the universe? Because it involves some slides I took out. Some people have stated and have observed that, look, if the laws of physics were just a little bit different, then we wouldn't be here. And that's fascinating. And therefore, they argue that the universe must have been designed so we could be here. But it amazes me that in a world in which we already know about natural selection and evolution, that people ask that question. The Earth wasn't designed so life could exist on it. Life arose on Earth because it could. Okay? Our universe wasn't designed so life could exist. In fact, life can't exist in life like us can't exist in most of the universe. Most of the universe is incredibly hostile, and in fact, the universe is trying to kill us all the time. One day it'll probably succeed. So the universe wasn't created so life could exist. Life evolved in our universe because it could. Life evolved on Earth because it could. Now, if there's a multiverse, of course, that makes the question even more interesting, because in other universes in which galaxies don't exist, maybe there are life forms that are quite different than the life forms we know about. Those life forms would be creating physics and talking to audiences, saying, why are the laws of physics in our universe just so perfect so we can be here? There must be a God, okay? But, of course, that's their universe. But even if without a multiverse, and some people say you invented the multiverse to get rid of God, that would be wonderful, but that's not why. The multiverse, again, physicists were dragged kicking and screaming to the multiverse because most of us would prefer there to be one universe and understand exactly why it has to be the way it is, rather than say the laws of physics are an accident. But even if there's just one universe, again, life exists on Earth because it could, but we don't know enough. We know of one kind of life. We have no idea of the kind of possibilities that could exist. And in my book, and I almost present a picture of my favorite science fiction story called The Black Cloud by Fred Hoyle, who is an astronomer. It's a great book to read, written in 1930 or something. It really captures how science is done. But ultimately, it involves the discovery of this cloud of gas, which astronomers realize is intelligent. Okay? And I once used to have debates with my friend Freeman Dyson about the nature of life in our universe, and he was the first one to convince me to read The Black Cloud. So even in such a universe, every form of life may wonder why the conditions of that are created so it can exist. But the answer is it can exist because those conditions are there. It's exactly the same for the universe as it is for life on Earth. And I don't know why suddenly people forget to think about life on Earth when they suddenly think that just because, the laws of physics are, if they were different, we wouldn't be here, somehow is a sign of divine intelligence. And the final thing I will say is, in fact, I can show that if the laws of physics were a little bit different, the universe would be more conducive to life in certain cases. So it's not as if we're in the ideal universe for life. If there were no dark energy, in the long term, life could, and so could my battery. Anyway, so there's no evidence for intelligent design. Let's enjoy our brief moment in the sun and not create silly reasons for why we're here, but rather enjoy being here as I've enjoyed being here with all of you. Thank you very much. I guess I'll sign some books too. Thank you. I really appreciate your interest and patience. Thank you.
I hope you enjoyed today's conversation. This podcast is produced by the Origins Project Foundation, a non-profit organization whose goal is to enrich your perspective of your place in the cosmos by providing access to the people who are driving the future of society in the 21st century and to the ideas that are changing our understanding of ourselves and our world. To learn more, please visit originsprojectfoundation.org.